Vilaplana from Universidad de Cartagena. Welcome.
Thank you. Well, first of all, let me thank the organizers for the nice opportunity to be here, explaining or talking about our work. So I also have to say that this is my favorite slot to speak, because it's after lunch. So if I see people falling asleep, I do not have to blame myself. It's the after lunch slot, so it's the only slot in which I'm happy for seeing people asleep. It's not my fault. So I try to think in this way. So yeah, thank you very much for the organizers for giving me the opportunity to talk about the work that's in collaboration. We'll talk about some papers, but in collaboration with Arpit Das, that is postdoc in Edinburgh, with my student Pablo Saura at the Technical University of Cartagena, and with Germán Sierra at the Institute of Theoretical Physics in Madrid, that he's here in the audience. So yeah, so let me put into context. Probably it's not necessary after last week talks that I regrettably I was not able to come here last week, is to put into context the idea of this modern view of about the global symmetries in quantum field theory that are related with the presence or implemented through topological operators. Right? This is the famous paper by Gaiotto, Kapustin, SAIFR, and Willett, something like 10 years ago. So basically, is the idea that these topological operators are defined on some codimension 1 surface. So are topological because the formations of this surface in which they are defined do not modify the correlators, right? Yeah, in these pictures, I'm assuming that for the moment we are thinking in the group-like symmetries in which these operators are labeled by the group elements. Then we have another operation that is the linking operation. If we have these topological operators, we have local operators in our theory. When we cross these defects, topological operators, we have the defect, and then we have the implementation of the symmetry operation on the local operator. Okay. So, and then we have another interesting probably thing is that you think about these operators in the same time slice. You can fuse it, and these topological operators are labeled by the group elements, and the group, and then the fusion between these topological operators give the new operator labeled by the group multiplication law, right? So, and the thing is that the point of view of this paper, as far as I understand, the conclusion of this paper is that to have the position and think about if you have theories in which you have topological operators, you can think about all the topological operators implement some kind of symmetries. And then there is something that is called, I will not enter into how appropriate is this name or not, is about something called non-invertible symmetries. Right? Non-invertible symmetries is that if you have theories, for instance, the kind of theories I'm going to talk about is rational conformal field theories in 2 dimensions, are plugged by this kind of topological operators. And of course, they have the properties of linking being topological, as before. But now in the fusion between these objects gives something that is not ruled out by the group multiplication law, or something more general or more, let me say general, that is a fusion category composition law. It's basically saying that when you compose 2 of these guys, you have the result is something like, as nicely is said in the review by John McGreevy, is a weighted superposition of these objects with these multiplicities, fusion multiplicities. Right? So I will not enter too much into the some points, but basically one can say that there is some tensions between the common law of this what an operator implementing a symmetry should be or not. But for instance, if you choose something like here B is the conjugate of A, right? Then you have here A conjugate A. So basically, if in this superposition you have more things that conjugate A identity, you have something, a tension with you have more things, so you cannot say that this composition of two conjugate things go to the identity. So this is the reason you can go to, or maybe you can call it, if you want, non-invertible symmetry. Okay. So yeah, so what the objectives of these works is that when you have a quantum field theory with global symmetry, it might be interesting to understand the composition or the structure of the Hilbert space into irreducible representations of the symmetry. Right? It is something in which I've learned many things for doing this. And yeah, what you could say, okay, how can we do it? And here, entanglement is going to be used in order to probe this structure of the how the symmetry organize the Hilbert space of your theory, right? So it is known that there is a way of using entanglement in field theory in conjunction with symmetries in something called symmetry-resolved entanglement entropy. It's more or less saying that this quantity quantifies the amount of entanglement for different sectors of your theory, right? So I will try to show here some results, trying to generalize this. There are results known for group-like symmetries, trying to generalize for the case of non-invertible symmetries, and hopefully very soon, depending on the agenda of my student, we will be able to put some new results on arXiv. Okay. Okay. So I will review some concepts that might be of interest in order to understand what we have done. Is the computation of entanglement in quantum field theory, right? So in the field theory, you have considered that this is the full field theory. We consider the full density matrix, and we consider some region A and the complement B, right? So how can we quantify the amount of correlations between the region A and the rest of the system? This is done by using something called the Renyi and the entanglement entropies. This is the Renyi entropy, basically. That is basically taking the reduced density matrix of your system, subsystem of interest, by taking the trace over the complement. You have this pictorially is so in this way. And then you use something like glue together these things, right? This reduced density matrix to n replicas. This should be something like the pictorial representation of the two replicated thing, right? And when you build this object, then you make an analytical continuation to n equal to 1, and you obtain the von Neumann entropy. That is the quantity that quantifies the amount of quantum correlations that are between a region A and the complement B, right? Okay. So, yeah, what happens when you have normally this thing is more or less has been done for the case of conformal field theories, etc. So, what about this symmetry-resolved entanglement? Right? Consider you have, for instance, a conformal field theory in 2 dimensions, only for having something in mind, within a global abelian symmetry given by implemented by discrete group G, right? So, in this situation, we have a charge operator, this mathematical Q, which eigenvalues are one-to-one correspondence, or are the irreducible representations of the group R. So if you consider the full density matrix of your theory, you have a unique ground state in your theory. This is an eigenstate of the total charge, so this thing commutes, right? So you can decompose this global density matrix in terms of these projectors. So projector to the R eigenspace of the total charge, right? So basically, this can be decomposed in something like this is the probability of being in this charge sector, and this is something the reduced density the density matrix corresponding to this charge sector, right? So Yeah, basically this probability is given by the total trace of this projector over the density matrix. This given, normally I put this because for convenience, right? Where this is the multiplicity of the representation R, this is the dimension of the representation, and this is the total volume of the group, right? Okay. That's true. That's true. That's completely true. Right. So, yeah. I mean, if you think of if it's a discrete abelian group, it's 1. All the representations are 1. Okay, I will comment on this later. Yeah, but for sure. Okay, and yeah, Javi, you're completely right. Yes. What he's saying is that the most general thing is that this. Sorry, it's not appearing. Okay, this denominator is the sum of the squares of these things. Okay, that's true. This is only, yeah, this is for a concrete phase of the theory. That's completely true. Okay, so once you have this decomposition, then as we are going to measure entanglement, here entanglement is not related with any quantum information operation or something like this. It's in order to, basically, you have to probe some properties of your field theory. You can only have access to some region, right? So you have to trace over the complement, and I will say that this tracing should be compatible with the decomposition of this total charge operator, right? This is something I will enter much a little bit later. But once you are able to take this tracing over B, you have just your reduced density matrix now has this form, decomposed into blocks. We are interested in computing entanglement for each charge sector, right? That is given by this symmetry resolved Renyi entropies. So basically, it's a Renyi entropy for the sector R, right? It's given by this thing. So there is an interesting phenomena that could happen, is that called entanglement equipartition, was put in this, proposed in this paper. That is what the entanglement entropy for all sectors is independent of the sector. So basically, all the entanglement is equipartitioned along all the sectors, right? Okay, so for convenience, I also will say that you can define something like called a replica partition function or entanglement partition function as a fixed value of the charge. This is given by this, in this form, is the trace over rho A n in the sector R. This is Q, this is the modular parameter of the replica manifold. It will be more clear probably later. So basically, the things that we want to compute is something, basically taking the operation of taking the log of this ratio of partition functions. Okay, so is there any question or comment at this point? Yeah. The assumptions. I mean, for instance, one thing. For instance, if you are considering the case we have been slightly commenting, is like imagine you have a group. Is a global. Is a group, right? It's a discrete group. All the representations are equal to 1. So basically, you will see at leading order. I will comment on the result. At leading order, the entanglement is equal for all sectors. Yeah, there are exceptions. Namely, I'm going to show that in the non-invertible case, the normal thing is that you break the equipartition, and always happens for non-abelian groups. But in the non-abelian group, I have something to say. Okay. Okay. So there are cases in which there is exact equipartitions. For instance, in the free boson in the circle, but normally the equipartition is only seen at leading order, right? I will comment. Okay. So now, in order to let me make something. I don't know if this is a combined or not. This should sound something like a digression. But it's important to introduce a way of computing the entanglement entropy through something called boundary conformal field theory approach. And then I will mention something probably is well known here, is the talking about the topological lines in rational conformal field theories. That is the kind of theories I'm going to talk about. So, related with the boundary conformal field theory approach, in 2 dimensions, when you take an interval, well, the region you are interested in is an interval, right? When you take an interval, A, this implies a factorization of the Hilbert space between HA, HB. Normally, in many papers, it appears this thing. That's not too much care about that. You have to impose some boundary conditions at this small disk of size epsilon. This is the size of the interval. You have an epsilon is a cutoff, you know, that separates between A and B. Where you are in a quantum field theory, you have to put a cutoff. It's important to put these boundary conditions, right? This is what Omori and Tachigawa says in a nice paper called Physics and Entangling Surface. So normally this thing is forget, but this is important. You know, it's basically, imagine that you have a conformal field theory and you take an interval and you put boundary conditions that break the conformal symmetry. So immediately what you are going to compute is not proving the conformal symmetry of your theory. So how you put boundary conditions that preserves the conformal symmetry, right? Okay, so anyway. Well, exactly. Yeah, for instance, yeah, this is also a very good point. For instance, when you do the calculation with twist fields, with the technique of twist fields, they are not going to see this boundary condition thing. So in our calculation, we will have a remnant of this boundary that is called the Affleck-Ludwig boundary entropy. But this, when you go to make a normalization group, this thing disappears, right? Yes, when you compute modular information, these things are going to disappear. Yeah, for sure. So, as far also the cutoff dependence is going to disappear also in the modular information. This is why people likes to compute modular information. Okay, so the thing is that when you did this in this geometry, imagine that this is a torus. You make a conformal transformation, and you can transform. Cardi show us how to do it to transform this geometry into the annulus, right? In which you have something. You will say something like you have 2 boundaries with boundary conditions alpha and beta, and you have this is the size of the annulus that is given by this is related with the size of the interval, and this is the modular parameter of the annulus. This is the modular parameter Q, right? And this is after some S transformation, you modify into this Q tilde that is basically given in this way, right? Okay, why is this useful? It's useful because basically computing the things that you need to compute the entanglement entropy amounts to compute some amplitude, transition amplitude. It's something like you can think. See, I don't know here there are stringy people. You know, it's something like it's very well known in string theory. You have a closed string propagating from this boundary into this boundary, right? This is the closed string propagation, right? This L0 is we are in conformal field theory. Sorry, this is basically the Virasoro mode L0 related with the energy of the Hamiltonian. So basically, it's a Hamiltonian evolution from here to here, right? And then you can write, once you compute this, that is more, I mean, it's quite easy, you can compute this. You see that this is an amplitude between 2 boundary states. These 2 boundary states are called Cardi states. These are basically the states that implements the symmetry that you don't want to break when you are taking the interval. So basically something that, if you are in conformal field theory, are states that preserve the conformal symmetry. An example is that these Cardi states are built in terms of Ishibashi states. These Ishibashi states are these states that have the same left and right movers, right, of the Virasoro algebra. Okay. Good. So this is, I mean, we know how to compute this, and now we go to the topological lines in rational conformal field theories, right? So we are going to use the simple setting. It's diagonal rational conformal field theory. That is field theories with a finite number of primary fields, and the Hilbert space is decomposed in these Verma modules that is given by this decomposition of the Hilbert space, right? So And when you consider the partition function, right? The partition function is computed in terms of taking the trace, right? And I read it that this is the torus partition function. I put here the insertion of the identity, right? And you can see that this partition function is basically the sum of all the primaries, all these characters of the theory. Right? Okay. So now, in these theories, it's interesting because there are something called it's very easy. I mean, you always will find, at least for rational conformal field theories, you will find something called these modular fusion categories, right? These modular fusion categories are given by some kind of topological defect lines in this dimensional line operators, right? That called Berlinde lines that are in one-to-one correspondence with the structure of the primaries of your theory. So basically, you have a finite number of primaries, you have a finite number of these Berlinde lines, and these famous fusion rules are given inherits the structure of the operator product expansion of the primaries of your theory, and it has this structure. And these multiplicity fusion coefficients are given by the famous Berlinde formula that it can be written in terms of the S matrix of the rational conformal field theory. So how this thing acts on the, not putting only drawings, if you want to see how this thing acts on this primary, the primary A, and this is the Berlinde line B, acts basically given the same primary with this factor. Right? So when you compute, for instance, the expectation value of this Berlinde line with the vacuum, gives you this term that is what we define as the dimension of the quantum dimension of the line. Right? Okay, this is basically something. And now for something that I need to use is talking about inserting Berlinde lines along the different parts of the torus. Right? When you insert a Berlinde line along the spatial circle of the torus, the partition function is this picture, is this decorated partition function that basically can be written in this way. You know, basically doesn't do anything radical on the structure of the partition function. And you could say that something, this is only the coefficient you're selling. Basically, you are computing something like the expectation value of this charge operator, if you like. I will not enter into the discussion. But then, if you insert this topological line along the temporal dimension, this decorated partition function completely changes, right? Because this is a defect partition function, and now you have to take the trace over the defect Hilbert space. This is a completely different thing. And now you see that the insertion of this topological defect, basically this decorated partition function, you know, we are mixing different sectors of the structure of the theory, right? Okay, but this happens. It is very well known since in the 90s, right? Okay, so this basically, I mean, this is terminology. I'm sorry because it sounds a little bit of digression, but you know, it's only terminology. And now with these tools, I mean, there is any question on this or yeah? You mean this formula? This is the famous. This is the Berlinde formula for rational conformal field theories. This is the. I don't know how we want to arrive to the Berlinde formula. I think it's yeah. Because, I mean, equalities, I mean, there are different partition functions, right? Sorry. These two one. Yeah, this is, oh, sorry. This is, I don't know why I put this. Yeah, this is a S transformation of the, it's an S transformation, right? But probably you need to do these things in order to arrive to the Berlinde. Probably, yeah. I don't remember the proof. Okay, so now what about the symmetry resolve? Basically, we are saying what is the structure of a Hilbert space of a theory? We have a global symmetry given by a group, and then basically what we have, or what we need, is two things. Is that what are the projectors to find the correct sectors of the charge of the theory? And the second thing is how to take intervals without breaking the symmetry that we are going to prove, or we want to prove. The first thing is that in abelian group J, the projectors are given in this form, right? It's the sum over the elements of G with these elements, these topological operators with this label G, and this H representation, you have dr, right? They have the dimensional representation over this number, right? So you can take the partition function representing your theory in the torus that is given by this, and you have the sum over these sectors, right? And now what we're going to do is, okay, for each one of these decorated partition functions, we're going to take the interval. And now, basically, we're going to have these decorated or entanglement partition functions. But now we have the boundary conditions. The boundary conditions should be something like we preserve conformal symmetry, and we preserve the global symmetry that we need to preserve. If you break, basically, imagine that you have a topological operator, and then you take some boundary conditions, you cut the Linde line, so you will create some charges, right? So basically, you are breaking the topological line. So you cannot do this. You have to allow that the topological line is able to end in the boundary conditions that you are imposing, right? Okay, if you write the modular norm of the annulus expressed in terms of the original torus parameter, right? You can see this implies that basically your approximation to the size of the interval is much bigger than the cutoff. It amounts that the spatial size of the torus is much bigger than sometimes it's called the high temperature approximation. Right? Okay. The thing is that basically people know the projectors, and the thing is that what are the boundary conditions that we need? Right? The boundary conditions we need now are written in terms of our Carrier states and are labeled by these J's. The thing is an interesting concept. It's the conformal boundary, a conformal boundary state B is the strongly symmetric. There are notions of being strong or weak symmetric. It's strongly symmetric if for any action of this topological operator on this guy gives the same boundary condition. This is something about you can see in this propagation along the annulus is that you have this topological operator can fuse with the boundary B. Right? This is called a strongly symmetric state. For instance, when you have a symmetry, have tough anomalies, it means that you cannot find strongly symmetric states. Right? So basically, if you don't have strongly symmetric states, you cannot symmetry resolve. The anomaly does not allow you to symmetry resolve with respect to this anomalous group. Right? Yeah, I mean, this is a matter about this is something that we have to clarify, because if you tell me that yeah, it's interesting. Okay, I mean, if you want to do this with twist fields, in principle you won't see these problems with boundary things, right? But there is a famous paper that I will mention later, that is the Goldstein-Sella paper, in which basically for twist fields you have to dress the twist fields properly. Yeah, but the thing is that in order to dress the twist fields, you have to look at the structure of the defect Hilbert space. And the correct dressing of the fields amounts to have something called scalars in the defect Hilbert space. Anomalous symmetries does not have scalar operators to dress the twist field operators. So, but this, our thinking is that the boundary approach tells us many things that in order how to do things properly. But we can, if you want. Okay, so once you have the computation, then basically this ratio, the things that you need, is given by this term. This is the Affleck look the boundary, basically are G functions that are the overlap of the identity with these boundary states. This is basically what is going to give us, when we take the limits, proper limits, we're going to give us basically this universal part of the thing, and this is basically, this is a coefficient that goes to log when you make the analytical continuation, and this is the thing that is telling you you are in some sector of your theory. For instance, somebody don't ask me about the equipartition. Look at, basically these are, for each sector R, you have this that depends only on the boundary conditions, and if you have a group in which all the representations NR is the multiplicity, where the multiplicity NR is dr, basically this is dr squared over G, dr is 1, so basically you have what is called equipartition at leading order, because probably you have some subleading orders of order epsilon over L in which it depends on R. This could happen. Sorry? Yeah, you can do it. Yeah, you can do it because basically you can do an expansion over this nome, right? Basically, what we are taking is the limit in which Q tilde is going to 0. So, but if you can take still, you can have control in some terms in which going to break the equipartition. But at leading order, you have equipartition, right? Okay, so there is an interesting connection with the symmetry result density of states. The symmetry result density of states appeared in black hole physics, introduced by Harlow and Oguri, and then was conjectured for quantum field theories, and then Javier Molina gave a proof some years ago, right? That this is the structure, basically is another way of accessing information about your theory, right? You have the density of states at a high energy, right? And then what happens when you have a global symmetry, but you have, this is the symmetry resolved sector of the density of states, and is given by this famous coefficient. So basically, there is some kind of connection between entanglement and density of states. Okay, these are the results. And now, what happens when we have a non-invertible symmetries? Well, how much time? 20 minutes, okay. Yeah, so basically, if you want to follow, and we wanted to follow the things that are known for groups, basically, what do we need to, when we have a symmetry that is implemented or is described in terms of a fusion category or a modular fusion category, is stick to the same things, right? Is to find projectors, taking into account that the action of this Berlin line mix different sectors of the theory, and then to see if the notion of topological instability, this notion that when you have a topological line, in this case pertaining to a non-invertible symmetry, if you are able to cut this topological line without breaking and allowing the topological line to end into the boundary, right? Okay, so the first thing, fortunately, some people gave this definition. When you have a fusion category, a conformal boundary state is C-weakly symmetric, not strongly symmetric, if for any topological line in this fusion category applied to this boundary gives whatever, but at least you recover the boundary, right? So this is something, a point of view, something open string point of view, right? It's basically that the topological line, if this is your annulus, the other topological line, the rest of the topological line could be here, ends without breaking, continuous and continuous. So it's basically something that happens in this way. So for those that are lovers of the sophisticated jargon of category theory and blah, 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 it's not my case, these weakly boundary states form a category. That in terms of the category theory, this thing has the nice name of right modules of the fusion category. That basically means that you have weakly symmetric states if you can gauge your fusion category. And what does it mean that you can gauge your fusion category? Is that you can find some algebraic object called Frobenius algebra, that basically, I mean, I had a lot of time to understand what this thing was, but it's basically an algebraic object that is basically a composition of some simple lines of your theory containing the identity. And people in condensed matter, they have called this something like prescription to make anion condensation. Right? So when you have these algebra objects, then immediately, basically, you can do something similar what when you make orbifolding with groups. But when you have a group, you can make each part of the orbifolding, you can insert something group topological operators. But when you have to orbifold, that is the same as gauging, when you have to do this for fusion categories, you cannot insert directly topological lines by themselves, because this has a bad behavior. Because topological lines go, this topological line goes here, the other one here, and fuse and have a superposition. But if you can find an algebraic object, algebra object, you can insert and you can orbifold with respect to the object, because this algebra object gives you an algebra object. This is the definition of an algebra object. Right? Okay, so, and this is the definition, right? So basically, this is a less strict condition on a boundary condition to be able to do symmetric resolution. Of course, if you are weakly symmetric, of course you are strongly symmetric, but the reverse is not true. No, I mean, the less thing that you have to have for gauging, let's think about gauging, not symmetry resolving, but if you can gauge, you can symmetry resolve. If you can, a non-invertible symmetry is to be weakly symmetric. But sometimes you are strongly symmetric. Yeah. It's strongly symmetric. Yeah, it's strongly symmetric. Yeah. Yeah. So then you basically, I'm not saying why, because it's in magician, but our work was understanding this and then trying to find these boundary conditions, right? And then there are ways of finding in different cases, right? So, okay, and then, okay, what are the projectors? Well, the projectors, the projectors in these theories are more involved. We can define this kind of projectors in which basically this is a projector that twists the sector and then inserts another, horizontally inserts a topological line. You have this kind of insertion, and then these are projectors, but it's interesting that from these two sets, the relevant projectors we need are given by this. This has the property of being a projector. Right? Okay, so what we did is, is basically we computed the generalized twist sectors in the torus. That is basically computing this trace over this projector. That is basically doing this calculation. As you are in the torus, you can, after some S transformation, some bulk, making this fusion of things into the bulk, and taking approximations that are I can show you. Then we find, this coefficient multiplied by this decorated partition function, right? So now we find what are the correct weakly symmetric states. We take these decorated entanglement partition functions, basically based in these decorated states, and basically the result is the same as for the group like, right? But now we have this thing that is controlled by the conformal dimension of the twist sector. We have these twisted G functions, and then we have these coefficients that has the sense of being a multiplicity and quantum dimensions, right? Okay. The thing is that you could say, okay, but this is the symmetry resolution of the non-invertible thing, but this is not true, because these sectors. So we have to be sure that for the group-like case, a projector to the R representation is a charge, right? But the question is that if this thing is a charge, is an irreducible representation of your fusion category? And the answer is no, right? The nice thing about doing this work is that at least these are the Lego, these are the Lego pieces to build this representation. Okay, so we have to go to the generalized charts, and then that are irreps of the fusion category. You know, for group-like symmetries, the charts operators are charts transformed in representation. So charts are detected by linking or something called lassoing with the symmetry generators. Basically, you have the local operator, you make these lasso actions with this topological operator, and then you have this detect if the operator is charged or not with respect to this thing. Okay, so the thing is that we'll replace this for non-invertible symmetries. So basically, the generalized charts are basically representations of a non-invertible symmetry are the lasso action on operators. We are going to do the same as in groups, right? We're going to lassoing and see how this lassoing action organize the different operators on your theory, right? Basically, this algebra, this lassoing operator, this is called something called tube algebra, right? Basically, the reps mu under this of this algebra are the irreducible representations of the fusion category. But we are following the steps of something we know from groups. So basically, let's do the same for non-invertible symmetries. Right? Okay, I could avoid to the following slide, but you know, basically, if you are able to find, we are not, some clever people did it, right, some time ago, to find the reps, what are the reps of these fusion categories. There is something like a modern view about how these reps are represented in different ways, is that the reps of this tube algebra are bulk anions or something called the terrific number of dream field center of a symmetry TFT, right? Something like the Turaev-Viro theory, right? It's basically that you have a quantum field theory with the local operators and you have topological lines. So you can decompose this field theory in something that is something like an interval, a topological theory living here. We have anions, mu, that are the irreps of this tube algebra, in which, you know, the ending of these anions in some boundary condition gives you the content host, the topological lines, and then the other ending gives you what are the operators. But the important thing, you know, for us at least is that it's very, we can have access at what are the real, what we call the generalized charts of a fusion category, right? So once you have this, for instance, it's very easy that in two-dimensional rational conformal field theories, this dream field center is basically this quantum double of the fusion category, and these irreducible representations are given by this order pair CD, where CD are simple lines of your category. The mu is the representation and the dimension of the representation. No, it's a pair. They call it the Digraph-Witten theory. You know, these mu's are represented by something that is the representation and the dimension of the representation. Right? It's basically, yeah. Yeah, it's also important to have in mind this something like this number, the number of boundary lines of type A containing a bulk line of type mu or irrep is given by this number, and is given by this multiplicity, right? Basically, because mu is nothing more or less than CD, right? Okay. Yeah. So the nice thing is that we have computed, in some sense, we have computed something like these projectors to something that is, we computed these projectors before, and now computing the relevant projectors onto the irreps is nothing more and nothing less than sum over this, all the twist sectors, right? It's something like before this mess of tube algebras and blah, blah, blah. Basically, Which one? Yes, it's the link product. It's not the tensor product. It's not the tensor product. No. Imagine something. You know, imagine you have the Fibonacci category, right? The Fibonacci will have the identity, and there's this tau or Fibonacci. You have two anions. What is the dream field center of the or you know? The thing is that you can be misguided. You have only two anions, or only two irreps, but it's not true. The irreps of the category has 4 anions, and the 4 anions should be something like the anion 1 1, the 1 tau, tau 1, and tau tau. But that does not mean that the 1 tau is the same as the tau 1, because there is something called braiding, and the braiding of the things are different between. R prime? What do you mean? Okay. Are you referring to the group? Yeah. Yeah, yes. You know, I mean, a nice exercise is you can write this thing, and then you can collapse to the group very easily, right? So this is basically, the nice thing about this is trying to demystify it. It seems that this is mystifying, but this is not mystifying, but basically it's the same. But the group is only a special case of all these things, right? Okay, you have the projectors, and this is you know, they are the coefficients of the S matrix, blah, blah. You have these guys. Okay, but at the end of the day, the nice thing is that as we have solved these decorated partition functions for all these LIGO things, basically you can find this decorated partition function for the irrep. This should be something similar in when you have the group case, we have set QR. This is Q mu, right? And B can be constructed very easily from the sum over all the 2 sectors. And then I write it, well, we write it in this way, right? You have here these conformal dimensions are in the 2 sectors, right? And when you sum, basically, you have and you define the dimension of this irrep, this multiplicity is exactly this number. So basically, you have this, you build your decorated partition function or entanglement partition function, and then you take this limit, the limit q tilde going to 0. This is the limit in which the interval is much bigger than the cutoff. That is the limit of physical interest, of course. And then when you do this thing, the leading sector, that is, as many things happens in many parts of these theories, the leading sector is the identity sector. Right? This thing rules. Basically, you have these numbers, could be something blah, blah, blah. But at the end of the day, for Q going to 0, the leading term should be something in which A is the identity, in which A is 0 the identity, the conformal dimension of the identity. If you have a unique ground state of your theory, is 0. So this is the dominating thing, and you can write your decorated partition function in a very similar way as in the group-like case. Right? So basically, the symmetry resolve entanglement for the sector of the rep mu of your fusion category has your universal thing, the boundary Affleck-Ludwig boundary entropy, and you have the log of this thing. Okay. So this is basically the multiplicity of the rep, the dimension of the rep, and this thing that probably should be. Sorry, what? For a diagonal theory, I mean, yeah. It's basically this thing. It's defined in this way, right? But this basically can be computed from this fusion and dimensions of the. The multiplicities, yeah, could be, yeah. C? What do you? It's sum over the d mu square. Yeah, exactly. Yeah, yeah. Yeah, sorry for not putting the details. Okay. So again, for instance, it's as if the fusion category contains only the invertible topological lines, then this is one, and then you have something entanglement equipartition. This is the case of the toric code, for instance, right? But for instance, if you have something like Rebes-3 or Fibonacci or something, at least one non-invertible line, then at least one of these guys has dimension bigger than 1, and you see the breaking of entanglement equipartition even at this O1 sect. This is something that happens. You could say, okay, good. Yeah, I have to comment something, is that this result, more or less, apart from some definitions that we have to fix, agrees with the results on symmetry resolved entanglement, but basically on symmetry resolved density of states that you obtain, people in the audience, Valentin, the Fritz author and collaborators here, right? Our construction preserves bulk symmetries by construction, and generically preserves generically. This is basically to say that in our construction, the connection with symmetry resolved density of states is preserved anytime. So there are other papers that use something called a technique called boundary tube algebra. There were the Choi and collaborators, and Heyman and Kella, that I will say that yield different results, okay? So something I can say is that preserves boundary symmetries, and only in a special case where strongly symmetric boundaries exist, bulk symmetries are preserved. But still, the full bulk and ionic sectors are not recovered. So basically, I will not enter too much, but I will try to pictorially show what is the difference between the two approaches, right? What we do is we access the sectors by a fusion category. We find what are the multiplicities, take our boundary states, preserving of course, the bulk symmetries, of course, because the bulk symmetries is at least in our point of view, is what you want to probe. And then, okay, we compute these things and then go to entanglement. So we have projectors on the torus. The interval A is defined at boundary conditions and entangling points. So you use boundary conformal field theory as an auxiliary theory. And the bulk symmetries are preserved. The approach of the other paper is completely different. What they do is basically they take the interval, so they have the theory, they cut the interval and put very generic, not necessarily preserving any symmetry of the theory, and then compute. They do something that is to insert projectors, but in the interval theory. That is basically a dynamical, I would say, a real boundary conformal field theory. I would say the only thing I say is that yield different results, of course. Okay. And still, in this method, there is something that, at the end of the day, if you make an experiment or something, you will find what is the total entropy you have in your theory, right? It's going to give us two contributions, that the sum, for instance, this is the group, right? And you have this sum over the probabilities of being in different configurational, you have two charges here, you have two charges here, and this is measured by this sector. And then you have something like a Shannon entropy about the fluctuations between being in one sector or other one. In our result, this is guaranteed because it's exactly the same parallels, exactly, and you need the full number of chairs of your theory that is given by the irreps on the dream field center. So basically, the result is the same, parallels. In the boundary tube algebra, that's a very sophisticated thing, but still, you cannot recover in your formulas the full spectrum or the full number of churches. So I ask myself, if you will be able to do an experiment, there will be a mismatch, because at least you are losing something. Okay, time is up. So let me make a comment about non-abelian groups. is that this is the nice thing about boundary conditions, Javi. You know, in some papers, you know, in the paper of Goldstein-Sell and Calabrese, Duval, and Murciano, they compute the symmetry resolved entanglement using the branch twist fields for this group, the Wessel-Minot with the minimal models. And basically, this entanglement equipartition breaking was given by the dimension square of the representations, right? So this is, I mean, you could say, okay, an abelian group also breaks entanglement equipartition, and it's true. The only thing I want to say is that if you go to boundary conformal field theory, you will say that you are not able to find carrier states that are strongly or weakly symmetric with respect to the Berlinde lines of the Wessel-Minot with the model. So basically, according to boundary conformal field theory, you cannot symmetry resolve this thing. Okay, but you have all these representations. But if you restrict to this, let me say, subset of the of Berlinde lines with integer spin, you know, this forms a fusion category, right? This is a fusion category. So for this subset, you can find weakly symmetric states. So with respect to this subset, you can find weakly symmetric states in which you can symmetry resolve the entanglement entropy, but only to the reps with integer spin. Probably, I mean, it's nice that we are not in agreement, but you know. No, I mean, even in higher dimension, try to find the reps of the category and something like that. I mean, but I'm not saying this. I'm only saying about this example. Only to say, yeah, I mean, I know that you say that you can do it with this field. The only thing we are saying, probably in the next paper, is that you have to do it, but with twist fields, but properly. Basically, saying that you have to dress the twist fields a la Goldstein-Sell, but with a little bit of care. But probably we are wrong, but it's nice. Okay, a summary and conclusions. According to the other group, we are wrong. Okay, I only said we don't have the same results. Okay, we have provided some prescription to compute symmetry resolved entanglement for non-invertible symmetries. You have used the general HR sectors of the category, but can be ascribed to a symmetry TFT. I think it's interesting we extend the remarkable relation between symmetry resolved density of states. We have shown the not very difficult situations, but this can be extended to something more involved, non-diagonal rational conformal field theories and blah, blah. And at the end, okay, so we have some idea of that this, the origin of the entanglement, breaking of entanglement equipartition in abelian groups could have to do something with categories. But, okay. So anyway, thank you very much for your attention. Yeah, finish. Sorry? I mean, I try to do the easy things, right? So, yeah, I mean, in our construction, there is basically, you can say many things, but at the end, I haven't shown the examples, basically the tricritical and blah, blah, and you can compute numbers and blah, blah. But at the end, all these numbers has to do if you are able to find these carrier states, weakly or not. This is an algorithm to find it. You know, it's, for diagonal rational conformal field theories, is quite easy to find these things. In other settings, you have to find the correct carrier states. If you are managed to find it, you can do it. Right? Eh? Liouville? Mhm.